we're going to do problem 116 today. It's going to be populating next right pointers in each node. So let's see what the problem is about. We have a perfect binary tree where all the leaves are on the same level and every parent has 2 children. So it looks exactly like the example given. And that's pretty intuitive, right? Basically, every level is as fully populated as it can be, and it's as tall as it can be. So we're given such a tree, and we're trying to basically populate the next pointers, which means that if I'm at node 2 here, I should be able to walk over to node 3 using a next pointer. And at the end of the day, after you apply your algorithm, your final tree should look something like this. So we're basically making it possible to traverse the tree in level order. Well, you could do it before, but essentially what we're doing is making direct connections between all the nodes that are on the same level. And so you might think something like a breadth first search or a level order traversal here might do you some good. And that's definitely a viable solution, but we're going to be going over the recursive one first for this problem. So if you notice, the output is separated by hashes, and that basically just means that nodes that are on different sides of the hash are on different levels. So given a tree that's represented by an array like this, we want to return a tree that has 1 on the first level, or the 0th level, however you want to count, and then 2, 3 on the second, and then 4, 5, 6, and 7. So the recursive approach here is actually pretty elegant and simple once you understand the concept. What we're going to do is focus on the most simple case first. We're going to start at the root node, and then we're going to try connecting the direct descendants of us. So 2 and 3 are our direct children, so we can just simply walk to the left, walk to the right, and then connect them directly. That's very simple. But if we had a more complex tree, like this entire tree, then we run into a more complicated case, because what we have is 2 cousins, 5 and 6, and these aren't necessarily they don't have the same parent, essentially. So we can't just walk over to 5 and 6 and connect them directly. What we need to do instead is establish the bridge between 2 and 3, and then use that bridge to connect the 2 cousins. So we're going to walk over to 2, use the bridge we already created in the first step of the recursion to walk over to 3, and then we can walk over to 6. There's already a link there, that's no problem. And then we'll have one person standing at 6, and we know that we can walk over to 5 directly. There's already a link there, no problem. And then we can just connect 5 and 6. So there are basically 2 cases here. One, where the 2 nodes to be connected share a common parent, and 2, where they don't share a common parent. But other than that, the recursion follows very smoothly. So we're going to repeat this process on a perfect binary tree of any size, and it will just run to completion. So notice that this is recursive, right? Because of all the different subtrees that are involved. So if we're looking at a very basic tree like 2, 4, 5, it's a very simple solution, just connect 4 and 5. Same thing for 3, 6, and 7. If we're looking at a bigger tree, we do the same thing for all the smaller subtrees and make sure to connect all the cousins. So I'm just trying to hammer that recursive principle home. Okay, now let's get to the solution. So we want to start with our base cases first. And to do that, we can just check if the root is none. So if the root is not there, then we just want to return. There's nothing we can do if you're giving me an empty tree. I'll just return it back to you. Okay, now we want to check if we have 2 direct children. So if root.left and root.right. if we do have two direct children, then we just want to connect them, right? Because it's very simple to walk over to each of them. So we're going to do root.left.next equals root.right. Very simple. Now, we also want to check if there is a bridge for us to cross. Because if there is a bridge for us to cross, then we want to use that opportunity while we're here to connect the cousins that are below us. Otherwise, we'll miss the opportunity. So we're going to say if root.next, if there is a bridge for us to cross, we will connect the two cousins. So basically, we're saying root.right, which is 5 in this scenario, .next, which is this link, and that is connected to root.next, which is 3, .left, which is 6, so we've basically formed this link. So after we have done these very simple maneuvers, we're going to continue recursively. So we're going to do self.connect, root.left, and self.connect, root.right. And this is very simply just continuing this same technique for the left and right subtrees, right? Because we have to finish the entire tree. So after we've finished this entire tree, we're eventually going to reach a none or an empty spot. And then that's going to basically return all the way up and we're going to finish. So what we want to do is just return the root because we've finished inserting all the links at that point. So return root. And this should work. Let's see how it runs. Great. Okay, awesome. So this is supposed to be a medium problem. and it is a very popular interview question, at least according to the top interview question filter. But I try to do questions that I think are a little trickier and that not many YouTubers have covered so that I can help people with questions that haven't been covered as much as well. So the time complexity here is linear time, right? Because in the worst case, the tree will look like a big line. We're just going to have to go through that entire line of nodes, which would be n. And we're going to say it's constant extra space here, even though there is stack usage, meaning that at each stage of the recursive call, we're going to be using some memory. But the question says we can assume implicit stack space does not count as extra space. So that's fine. All right, thank you for watching. If you like this video, please like, subscribe, and comment. Thank you.